Good morning. Can all of you hear me? I'm hoping. It's nice to see everyone. My name is Aaliyah. I'm the events manager at the Science Museum of Minnesota, and I want to welcome all of our members to another great Member Appreciation Month program. This is our first virtual tour via Zoom, so you'll have to email us and let us know how it went. I'm going to start with a brief introduction. And first of all, I want to remind you this is part of our Member Appreciation Month programming, and we're offering programs almost every day at the Science Museum. So if you haven't checked out our website, please do visit smm.org/thanks. And if you scroll down, you can see we have programming almost every day, and you can search it week by week. So we'll be offering these virtual tours every Saturday, and it should be a lot of fun. So a couple of little Zoom notes before we get started too. I'll just recommend to all of you that if you're not already in speaker view, that's the best way to watch this presentation. So you're going to want to head up to the view bar over on the upper right-hand side and choose speaker view. That way you'll get a spotlight on the presenter when they're talking. Actually, I feel like I'm not in speaker view right now, so I just moved myself to speaker view. And then just a little bit about the program format. In a moment, I'm going to hand this over to Dr. Alex Hastings, our Fitzpatrick Chair of Paleontology, and you can see him right there on the camera. And he's going to take you on a virtual walk through our Paleo Gallery at the Science Museum. But before I do that, I want to tell you a little bit about the footage you're about to see. So I actually have to read out a little note I got from our exhibits head. What you're going to be seeing is something called Matterport footage. This is a model that is a virtual reality and augmented reality technique to engage visitors. The Matterport model was an experiment to test how engaging a virtual tour might be. We're very interested in what you think of this technique, and if you happen to have an Oculus, this model can be viewed in a true VR environment. So we will share the link to the Matterport footage with you today. Alex is going to use it to show you some of his favorite parts of the Paleo Gallery, but you can also visit the website later and tour on your own. So it's the closest thing you can get to the museum while we're still closed to the public. So right now, I'm going to go ahead and introduce Dr. Alex Hastings. He's our Fitzpatrick Chair of Paleontology. He joined the museum in 2018. After working as the Assistant Curator of Paleontology at the Virginia Museum of Natural History. Alex has worked on a wide variety of fossil projects ranging from dinosaurs to insects. He did his PhD work at the University of Florida, focusing on fossil crocodiles from South America. During his graduate career, he named 5 new species of fossil crocodile and helped discover the world's largest snake, the extinct Titanoboa, from about 60 million years ago. Some of you may have enjoyed his work firsthand in the Science Superheroes exhibition featuring a life model of Titanoboa. And before I hand it off to Alex, I do want to let all of you know that for the duration of the tour, you'll want to keep your microphones muted. However, towards the conclusion of the tour, we will open up for questions, and the best way to do that is to chat them into the chat window down on the bottom middle part of your screen. And now, with no further ado, I'm going to hand it off to Dr. Alex Hastings.
Awesome. Thanks, Aaliyah. Yeah, I'm really happy to be able to kind of guide you guys through this really cool kind of virtual capture of the exhibit space here. I'm actually talking to you from the Paleo Lab right here. And towards the end of this, I'll show you a little bit of the stuff that we're working on right now here. This is a fun, cool space. So what I'm going to do, and I should also say it's kind of our first go through this, so bear with us a little bit, but this should go well. I'm going to share my screen. I'm going to pull up the Matterport, which is going to allow you guys to see what we're doing, or where, and all right, we should be good. Let me just max this screen out. Great. Looking good. Okay. So what they did is captured a good 3D space. And because the Paleo Lab is actually right next to the exhibit space, we can actually start right here. I'll do a quick little spin around here. So this is the Paleo Lab that we're looking at. Um,
No way.
and it's actually
help us
decently
for a second?
clean, which is nice. It's not always.
Could you help us for a second?
But we are going to do mostly a tour here of the exhibits. So we can zoom ourselves forward here and walk on in to, go right there, the exhibits. So this is super cool and fun. This is a good three-dimensional capture. So what we're looking at is one end of the gallery here where we've got our lovely fossil rhino skeleton here, as well as preserved rhino bed. A lot of times when these rhino skeletons are found, they are like this, where it's a whole pile of bones all together there. Then you have to meticulously go through and pull these things out there. But from that, you can actually put together entire skeletons like this lovely little rhino right here. And if we spin around, we'll see something completely different. This is a nice case of different states of fossilization. Includes some tracks on one side. We got a nice fish here. There's a fossil feather. Some of you guys might remember this from the galleries. And let's actually take it from there to, there we go, our giant fish. So this is, of course, Zophanctinus. This is a really, really big, large fish that was swimming the ancient seaway that actually flooded from the Gulf of Mexico all the way up into Canada, and that split Western and Eastern North America. So you ended up having big, massive waterway there, and you get big sharks, you get these large marine reptiles, and some just bonkers crazy fish with these giant jaws of sharp, pointy teeth. So this is something that can get 10, 15 feet, even longer. And this is certainly a good sized individual there. So I promise you, if you were swimming in the Cretaceous Seaway, like say 70 million years ago, you would be absolutely terrified of running across this fish. It's definitely a big monster. Maybe not quite as terrifying, but still very cool. We've got some other fossil fish here that you may remember. This is a really nice block of gar fish. Now, gar, these, we actually have them around today. A lot of them kind of like a long snout. They're predators as well, so they have big toothy jaws. And one of the things that's interesting about gar is that they actually can kind of breathe air to a certain extent. So they have this ability to actually gulp air from the surface and get the oxygen from it, in addition to their gills that can process the oxygen in the water. So it actually allows them to live in oxygen poor waters. They can, if they get trapped in like a little lake during a dry season and the oxygen starts going down, they can actually get a lot of oxygen from the air itself and help them survive until, the rains come back and they can get into bigger, more open waters. So it's a really good survival tactic. And that's actually also shared by the bowfin fish over here. And you'll also see we've got a nice kind of sort of stingray relative there too. But of course, the big icons, the ones that you miss, I miss. We love seeing our big old dinosaurs. Whoa, sorry. Still kind of driving this. We'll just catch it from the other side. Here we go. We got the butt side of our Triceratops. Let's move over here. And one of the things you'll notice in here, we actually got these fun little kind of signs here that allow you to see here, it's pulling up the actual signage from the exhibit here. So not only are you able to kind of see those in place, but you can kind of bring those and pull those up a good bit bigger. So this is a good example of kind of how a lot of these skeletons are often a little bit of a composite, right? So they're typically, you don't find an entire skeleton with every single bone in place there. You usually end up having to fill in the gaps. And one of the ways that this has been done over the years is to take similar sized bones from other skeletons, or sometimes you find like just, one right arm bone, but you happen to be missing that in the skeleton that you found. So you can use that in place as long as the size is about right. So this is actually a composite of 8 different Triceratops. It's mostly just 2, but there are another 6 bones that were used to kind of fill in some of the gaps. there were still a couple of gaps even after that. So we went to casts or replicas from other skeletons to complete the whole Triceratops skeleton. But it's still a very, very cool, really, really nice iconic piece. This is from the Hell Creek Formation in Montana. This was dug up by the Science Museum, largely by team led by Bruce Erickson. Actually, I'm sorry for jumping around a little bit, but I want to call out, it was actually Lois Erickson, Bruce's wife, that found the first of these Triceratops bones here. So we're actually really happy that when we redid the signage, we dug through our photo archives and managed to find this really nice photo of Lois and Bruce working together at the site out in Montana back in the 60s when they found this thing, which is really, really nice. I like that our exhibits have, not just these big dinosaurs, but lots of other cool and interesting things kind of here and there. So one of our fun little pieces is, and we'll get a little bit closer, is this palm frond. Darn, I am clearly getting used to, maybe if I'll use the touch screen here, maybe this will be a little smoother. Is a palm frond that has a little fish, and I'll use the cursor here, a fish that was actually preserved with the palm fronds. This is all in one big slab here, and it's a real challenge to get those things out in one piece. To get those kind of preserved together is really nice. So this is from an ancient lake, actually the same place, same area that those gar fish were found in, where you just get incredible level of preservation. Everything's basically, oh no, are we stuck? Okay, sorry, hold on for 1 second here. Am I frozen? You see it? Do you see the metaphor? Oh, you do? Yeah, okay. Never mind. Then never mind. All right. Sorry. Hopefully you guys are all seeing it, but definitely chime in the chat if you're seeing nothing here. We'll fix that. So really, really cool preservation there. Kind of coming in at our big Diplodocus. This is, of course, the big giant sauropod or long-necked dinosaur. These are the largest land animals of all time. There's never been anything that's gotten bigger than these big long-necked dinosaurs. This is much bigger than elephants and giraffes and all that great stuff. And there's actually some really fascinating, fun things to figure out on exactly how and why that happened. Some of the why seems to have been a bit of what we call an evolutionary arms race. This is where kind of the predators get bigger, so the prey get bigger too, so that they don't get eaten by the predators, which then get even bigger and bigger and bigger and bigger. And part of the reason that was possible is because the climate through much of the age of the dinosaurs was not only very warm, but it was also pretty stable. You didn't see these big changes. You didn't have ice ages or anything like that throughout really the whole age of the dinosaurs. And thanks to that stability, you get to see just crazy weird stuff happening, like giant reptiles really getting to be the largest animals on land of all time. Some of the logistics, and forgive me, I'm gonna zoom over here, of how that happened is actually really, really fun growth. So when you think about something that has to start as a little egg and grow to be the biggest thing that's ever been on land, there are actually limits on how big the baby can be when it comes out of the mom, because you still have to have an egg, right? So this is whole reptile lineage that led to these dinosaurs are still laying eggs, and there's limits on how big an egg can get. There's a couple of issues you got to deal with. One is the egg has to be strong enough to hold up its own weight as well as the developing baby inside, right? So if it gets really big, the shell needs to get thicker in order to hold itself up, right? However, there's two problems. One, the baby has to be able to get out of that shell, right? So that's a big issue. So if it's really thick, that's going to be a problem for, a comparatively pretty weak little baby. The other piece is that they still actually have to respire. So oxygen still has to get into the egg itself. So if the shell is really thick, it's going to be hard for oxygen to get in there. And of course, if you're bigger, you need even more oxygen. So there's a balance that has to happen there. And as a result, the egg of one of these even really, really big dinosaurs is really, even smaller than a basketball, really. And that's as big as they can possibly get. So they have to start off as this little tiny thing and get very quickly very big. Otherwise, they get eaten, right? So what you see is a different style of growth entirely in most of these dinosaurs that we call isometric growth, which basically just means they stay essentially the same proportions as a baby all the way into adulthood. So this is really different from something you see in like us as people. Human babies usually have really big heads. That has a whole thing to do with brain development and stuff. So thanks to this very different style of growth, though, they're able to grow very, very quickly, very, very big by just basically doing same thing bigger throughout their life until they reach these massive adult sizes, which is really fun. And some of that research is actually thanks to Dr. Christy Curry Rogers, who's currently a professor at Macalester College, but is actually used to be here at the Science Museum as well, which is really fun. Spinning around to what we sometimes refer to as the Jurassic Island. These are a couple of dinosaurs from the Jurassic period. These are from fieldwork around particularly Utah, but also Wyoming, where we've got the one icon of the Jurassic, the Allosaurus. Now, this is long before there was anything like a T-Rex. And it was actually the largest predator of its time. So one of the easiest ways, if you ever want to tell an Allosaurus apart from a T-Rex, easiest, quickest way, T-Rex had 2 fingers, Allosaurus had 3 fingers. So 2 and 3. So if you got 3 fingers, you know it's not a T-Rex. There's a good chance it's going to be an Allosaurus. We actually know this species really, really well because there have been dozens and dozens and dozens of fossil skeletons of Allosaurus found, particularly in like Utah, but also in most of kind of the Western North American states. And as a result, we know a lot about not only kind of how they lived and grow, but we've also found, interestingly, lots of bite marks on bones of Allosaurus that were made by other Allosaurus. So we actually know that these things were actively eating each other as well as the other dinosaurs of their environment, which is crazy. And then the plant eater right here is Camptosaurus. And this is kind of a predecessor to things like duckbill dinosaurs. And we actually have another skeleton of Camptosaurus that's lying down right here. Again, really, really nice, high quality stuff. And this is essentially all one original skeleton. Just to bring up some Minnesota, we've got this very lovely, large Endosaris. Now this is something kind of like a squid, but had this big, long, straight shell. And these can be found right here in the metro area of Minneapolis-St. Paul, including this one right here. And some of these things could actually get even bigger than this. This is about like 8 feet long. We've got even bigger ones, or especially ones that are fragments, but would have been even bigger than that, like over 10 feet long. And these things would have been predators, essentially, so kind of picking things off of the seafloor. Exactly what, we're still kind of figuring things out. There's actually a whole conversation to be had about even how many arms they would have had, or if they would have had suctions on them. So there's really fun conversations that we can have about Endosaris, but this is a really, really cool fossil that got really big and lived right here in the cities about 450 million years ago, which is way older than the dinosaurs, which makes it really cool. Let's get some other highlights right here. So coming up to what I refer to as the head case here, we've got a bunch of cool dinosaur skulls on display. And one of the things we did with the more recent signage in 2019 is show a little bit of the kind of evolutionary relationships between these dinosaurs, because you got a pretty good spread of what kinds of dinosaurs have lived throughout time, mostly in North America for this case, but a couple that weren't. So you've got things like the long neck dinosaur, Camarasaurus. This is similar to Diplodocus, but it would have actually been able to hold its neck upright. Plesiosaurus, which is kind of an early ancestor to that. We're actually going to be getting a whole skeleton of something very similar to Plesiosaurus in our exhibit space very, very soon. So hopefully with the reopening, you guys will be able to check that out. That's a little bit of a teaser. Dilophosaurus, became famous in the Jurassic Park movie, the first one, as the thing that had a frill stick out of its neck and it spat venom on the bad guy. There's actually zero evidence for either venom spitting or the frill sticking out of the neck, I'm sorry to say. It's a very cool idea, but it did have the big head crest there, and it's actually larger than the one in the Jurassic Park movie, which is kind of fun. We've got some horned dinosaurs. We've got Stegosaurus. We've got duckbill dinosaurs that became really, really abundant throughout the age of the dinosaurs. A little bit of a spread of things. Let's just move over here a bit. I really actually, so this might not look like the most amazing thing, but this is actually, these two pieces are absolutely incredible and essential to, I'm not exaggerating, life itself. Particularly this one right here is a section of what's called the Banded Iron Formation. And these were largely built up, basically layers of mud built up by a extinct kind of bacteria. This is so far back, this is over 2 billion years old. So far back that there's literally not even like things that eat other things. That's how quote unquote simple the ecosystem was back then. And that far back, there really wasn't even much oxygen in the atmosphere. But because these bacteria were photosynthesizing and there's nothing to eat them, they just went all over the world and started basically pumping oxygen into the atmosphere as a result of their natural processes. And that oxygen has more or less been cycling in and out of the atmosphere ever since. So that huge amount of oxygen that we are taking advantage of every single day here is really thanks to bacteria billions of years ago building that up. Now, because it's so old, there's not a lot of places in the world where you can actually see these, but Minnesota actually has one of the best records of these ancient creatures, largely in kind of the northern part of Minnesota. So we have some of the oldest fossils in the country and even really in the world right here in Minnesota. And that is really incredible. So we've got a really old one here. We've got a younger one that's this big piece here. Some of these things got to be absolutely massive. And I'm getting the wind to kind of start bringing this together here. So we'll make our way back to Paleolab and then we'll show you some of the stuff we've got here. But as a crocodile lover, I can't walk past this beautiful Gavialosuchus skeleton here. Now, this is from some work that my predecessor, Bruce Erickson, did in South Carolina and helped find one of these really, really complete, really, really large seagoing crocodiles that used to live in South Carolina. Some refer this to Thecacampsa, Gavialosuchus. That's a whole other nerdy science conversation there. But regardless, it's a big, giant crocodile with powerful jaws and may, in fact, have actually been eating the occasional small whale, which is really, really, really cool. Let's just walk by. Got a couple of fun little dinosaurs here. This is Bambiraptor. This is really, really tight on the birdline side of dinosaur evolution. So we think it would have been covered in feathers. And one of the things that really shows off its birdiness is actually the furcula, which is the wishbone. So you can actually see a little diagram here of the wishbone of Bambiraptor. That's a really good sign. This is something that kind of bridges those muscles on the chest there, and in birds ends up being really important for developing those muscles for flight, which is a really fun connection in evolution between these. This is a Compsognathus skeleton, which is one of the earlier it's from the Jurassic period of actually Europe. It's a really cool little dinosaur. Despite not being that big, there weren't really a lot of larger predators, so it actually probably would have been doing just fine despite being pretty small. As we walk by on our left here, we've got a case full of some things that are largely in South Dakota, Nebraska. And this is from the age of mammals. This is after the big extinction of the dinosaurs. Mammals start going nuts, going into all kinds of crazy different things. We start to see some things that really look familiar. So we're getting things like Haplophonius here, which is this kind of saber-tooth looking cats. We're also getting things like big old tortoises roaming around, and some little kind of deer looking things, some hyena looking things. These are roaming the growing grasslands of Nebraska and South Dakota. And we have some of the really, really good fossil examples of them right here at the Science Museum. Let's see, how are we doing? Time we're, okay. All right, we'll kind of come back around here, and I'll show you some of the virtual space here because it'd be a little bit easier to show you in here too. So we can walk seamlessly into the Paleo Lab. One of the really nice things is when we can reopen, we can actually open these doors, and people walking through can actually see what we're working on here through the lab, and we're hoping to get that going when we reopen, at some point when we reopen. But since not all of you maybe have seen this space here, we've done a little bit of reorganizing. We've of course got some modern stuff here. So we've got some taxidermy specimens. We've also got some skeletons around. These are fossil crocodile skull and jaw. We actually use modern stuff quite a lot. It really helps when you're dealing with little bits and pieces or scraps of fossils that you're trying to figure out exactly what they are, where they're from, what kind of animal. So having those modern animals can be really, really helpful for understanding exactly what we're looking at. Some bigger things in the room here. We've got our Hypsilophodon life model. This is something that was on exhibit. This is a really fun little plant-eating dinosaur. We've also got a, this one's kind of fun. This is a Stegosaurus pelvis. I think we can go right up to it. Yep. And it it's a Stegosaurus butt, for lack of a better term. So this is one of the things that's actually really fascinating about Stegosaurus is that this pelvis was held very high, actually higher even than the shoulders and the head. And that did a couple of things for Stegosaurus. It actually allowed it to keep its head relatively low where it was doing most of its feeding. So it was picking up all the low-lying plants there, while the big like long neck dinosaurs were going for the higher plants. But by having its hips so high, they actually kept the tail up high too. And that kept, very importantly, the tail, which of course has spikes on the end, at kind of locked and ready position for any predator that might try and sneak up from behind. So this is actually would have been held just in a nice kind of passive position at the head level of Allosaurus, which of course was the big predator of its time. So it means that while Stegosaurus is going around eating all the plants that it wants to, it's got this weapon ready to go to defend itself from Allosaurus or any other predators, just by the simple fact that it has its hips up high, which is kind of a neat adaptation. And spinning around here, that goes to kind of the rest of the collection. Sorry, spinning around. And feel free to cut me off first here. And this is some of the other stuff. We've got some more crocodiles. These are from about 60 million years ago from North Dakota. We did a ton of work, the Science Museum at a site called Wanigan Creek. So there's a whole other part of the exhibit dedicated exclusively to that ancient swampy environment. When not only were crocodiles really abundant, they were the top predators for their time. They're actually much larger than any of the mammals at the time. It's really, really cool, 60 million years ago, which is relatively soon after the age of the dinosaurs. And we'll actually, let's see. So this is a mammoth tusk that we brought in recently. It's actually being, okay, I'm being told to kind of start bringing things around. It's actually a whole job that we're going to be working on for quite a while because we don't want the whole thing to disintegrate, which it will if we don't. And I can actually bring you guys back pretty close to where we are right now. So I am speaking to you from this lovely corner here where we've got these bones right behind me. So with that, I will switch this over and we will do some questions that you guys might have about our cool space here. So I will stop sharing. And here we go.
All right. Thank you so much, Alex. I'm going to remind all of you we have time for just a few questions. So, oh, I already see some. So here's one from Alan saying, do you have any digs excavations ongoing now or planned? And how do you determine where to look?
Yeah, so the first part there, yes, we do have excavations that we are very much hoping to get back to. We had grand plans. I was supposed to be on 2 dinosaur digs last summer that neither of those happened. I'm gonna stay optimistic that I'll be going to both of them this summer. The first one is a Jurassic site in Wyoming that I've been going to for a number of years, where we're excavating out something a bit like a Diplodocus. It's a long-necked dinosaur. They're huge animals and they have lots of bones and they take forever. So this has been like a 10, 15-year project on the whole that I've been on a part of for part of that. Very much hoping to get back there. And then I've got another one that I started in 2019 with the Science Museum to go out to central Montana, where and this gets to the second part of your question, is figuring out where to look, right? So if you don't have an established dig site, where do you know, or how do you know where to dig? You got to go out and look. So what we did in 2019 was got a crew out there, picked an area that we knew there was lots of rock exposure from the right time. This is from the end of the age of the dinosaurs, from the late Cretaceous. And this is largely known thanks to part of the US government known as the US Geological Survey, that over the centuries really has gone out and figured out what kind of rock and how old that is throughout basically all of the United States. And thanks to that, we can be like, all right, we know there's some of the right kind of rock there, but you still don't actually know where exactly. So you still got to go out there and you just got to physically look all over the place. So we're hiking up and down and up and down and up and down. It was really good cardio. And we identified 19 different fossil sites in that area in central Montana. Really good for actual excavation. So most of them had just kind of little bits and pieces, not a ton of things. But one of them is definitely a bone bed, meaning that once we start opening that up, we're going to find a lot of fossils. And just from the stuff that was out at the surface, seems like we're finding either the big like Triceratops or something like a duck-billed dinosaur. They're pretty scrappy, so we're going to have to figure that out as we start developing. And we also found part of at another site, a pachycephalosaur. If you don't know that one, it's this big dome-headed dinosaur. They're so weird and cool. Ran around on 2 legs, had this really thick skull. We found that really thick skull, and we very much want to go back and see if we can find any more of it. So hopefully 2021, we'll get out there.
Oh, that's so great. So I'm getting lots of great questions here. So I'm going to do, we've got 3 more questions, I think, and we'll get through those. And if we have time, we might do one more. So the next question comes from Jack. Why do dinosaurs usually have long tails?
Why do dinosaurs have long tails? Actually, pretty much all of them had a decently long tail. Some definitely longer than others. So like the sauropod dinosaurs, the long-necked dinosaurs had really long tails, right? And mostly this is for what we call counterbalance. So basically imagine a big long neck dinosaur has this big long neck here. If you have a big long neck, that's going to weigh down that end. And if you didn't have something to balance it on the other side, you'd be running your head into the ground all the time, and that'd be super awkward. So having that long tail helps balance that out. But it has another advantage of it acting like a defensive thing. So you can use that long tail like a whip to just kind of smack the face of any predators that might come against you. So it can have more than one purpose. Now, if we look at something instead like TRex, that doesn't have a big long neck, instead has an incredibly huge head, right? Big giant head, massive muscles, very powerful jaws. The tail there is really much more on just the counterbalance side there. So it's helping T-Rex not just plant its face into the dirt every time it takes a step. That tail really helps it stay nice and even so it can move around nice and freely. So for most dinosaurs, it's going to be that counterbalance thing. A couple dinosaurs have developed cool things like Stegosaurus with the spikes on the tail, which is good defense. Ankylosaurus has the club on the end of its tail. So there's some cool, fun things that have come through dinosaur evolution in addition to that. But the counterbalance is a big one.
Okay, so now we've got lots of great questions. There's lots of great kids on the call. So this next
Awesome.
one comes from kindergartner Elizabeth. Will you have more fossils to show us today? And I'm wondering if you can tell us about the one right behind you.
Yeah, so we've got tons and tons of great stuff. So we might as well start with the one right behind me here. This is a string of vertebrae. So that's the backbone of the tail of a long-necked dinosaur called Haplocanthosaurus. Now, probably a little less familiar with that one. It's a lot like a Diplodocus or a Brontosaurus, a little bit different. But they're fairly unusual. There's not a lot of good examples. And we actually have a lot of the skeleton of this dinosaur. So this is actually just one small piece of what we have of Haplocanthosaurus. And this is actually a volunteer research project right now. So we're hoping to learn some more about Haplocanthosaurus thanks to the cool stuff we have here. We do have some other stuff too. Maybe we'll do like another question or two here, and I can quickly snag a couple things too that I can show you off too that we've got in the lab here.
Perfect. So the next question I have is from John, age 6, asking if you've ever found a caveman skeleton.
A caveman skeleton. I have not. So largely, so people have really only been around, depending on how you define a person, 2 million years or so. And a lot of what I work on is much older than that. So there weren't any people like during the age of the dinosaurs and stuff like that. I have done some stuff in places where you could find early people. Caveman usually ends up meaning Neanderthal people. And for that, you got to go to Europe or Asia. And a lot of my work from that time period has been from here in North America. You can find early people. I actually haven't run into any yet, but given a lot of my work in Minnesota has been focused on the time when people did arrive here, I feel like it's just a matter of time before I run into an old person for that sense. But it'll be fun.
And then how do you put together a fossil for display so that it doesn't fall?
Yeah, that's a whole art to how you actually mount an actual dinosaur skeleton. So if you take something like we just saw on the virtual tour, you've seen in the exhibits, like the big Diplodocus there, big old skeleton, it's got a lot of original bones up there on display. Now, when we do this today, we tend to have very, very careful, very kind of artfully done metal work that will hold those nice and securely so that nothing's going to fall down. They're also not doing any damage to the bones. However, some of our pieces have been up for 50, 60 years when people did things a little bit differently. So some of them actually had drills, kind of drill a little bit of a hole in there to get the metal rod in there. That is good in the sense that it secures it, so it's not going to fall, which is important. But it does do a little bit of damage to the bones, so that's something that we don't really do now. Sometimes though, a lot of times though, people move towards putting either 3D prints or casts on display because those aren't the original. You can go ahead and drill all the holes you want into them because you still got the original safe and sound. But whenever they do put the actual original bones up, they tend to do this very, very careful metalwork. And it's a very specific skill set that some people are just really, really good at. And we're lucky to have, excuse me, some of those people here at the Science Museum.
And I keep muting myself. I don't know why. Molly wants to know if you have a T-Rex.
So not only we have the T-Rex skeleton in the lobby, that is a cast skeleton, but we do have T-Rex actual fossils in our collections vaults. And these are from Montana, largely from the work that Bruce Erickson did back when he was collecting that Triceratops. So we got a few bones, including part of the brain case of a T-Rex, as well as some monster-sized toe bones and some other kind of bits and pieces. We got a good leg bone as well of T-Rex. So we do have some actual T-Rex bones too.
That's awesome. So folks, I know we're kind of over time here. So we have a couple more questions and we will not be offended if you need to log off, but I think Alex is available to answer a few more questions and maybe even show us a few more fossils. So hang on if you can. And if you're not, if you can't, we want to thank you for being here and let you know that we're going to have a virtual tour of our We Move and We Stay gallery next week with our anthropology curator, Ed Hastings, and one of our exhibit advisors on that project, Jim Rock. So sorry, let me just get to these next questions real quick. This is actually a question and a comment from Leon Park. Can kids ever volunteer to help at fossil dig sites? That would be my dream come true.
So the short end is, so like kind of a dinosaur dig sort of thing. A lot of those are, because we're not abundant in dinosaurs here, are happening in other places. So there are some sort of logistics, and there's only so many people we can bring out at a time. But when I went out to Montana, that was with a team of volunteers from the museum. So there is a limited number of people that can go out there. Tends to be a little bit more for grown-ups, but I've got some good news for you though, that there is a place in Minnesota where even the youngest kids can go out and collect fossils. This is a place called the Hill Annex Mine State Park. This is up in Calumet, Minnesota, up in the Iron Range. So it's about 3 hours from here. And in the summer, they run a fossil collecting program where anyone can basically come in, hop on an old school bus, take a ride over to where a bunch of fossils are coming out of these big giant mounds that were built up from the iron mines. And you can find fossils from 90 million years ago there. And a lot of them tend to be kind of like snails and clams, but they're like 90 million years old. But you can also find shark teeth, which is really, really fun and cool. And my favorite thing, you can actually, they're pretty rare, but you can find crocodile fossils there too, because we actually had those here in Minnesota 90 to 100 million years ago, which is really incredible. So this program wasn't run last summer because of COVID. We're optimistic that it'll be run this summer though. So check out, just a quick Google search will get you there to the Hill Annex Mine State Park, and you can get some more info on how to check it out and find your own.
All right, so Hill Annex Mine State Park.
That's right.
And I think now we're going to need to send everybody a link to our Matterport footage and a little information about that. So thank you so much. I've got one last question, and this might actually feed into Alex if you're able to show us any more fun fossils. Jack asks, can you, oh wait, nope. Jason asks, what in your opinion is the best fossil?
Sorry, so I'm like hearing action. Can you just say that one more time? Sure.
What in your opinion is the best fossil?
What is the best fossil? Oh my gosh, that's so hard to say. Let's see. So I'll answer like the best in general. I'm a crocodile fan. This is where like a lot of my research has been. I think they are the most wonderful, beautiful, amazing creatures that have ever existed on Earth. So finding a crocodile fossil always makes it a good day. However, there are some really incredible things that we have specifically at the Science Museum. I would say the most incredible thing that we have in our collection is actually it's not on display because it's so fragile, it's so delicate and so important for science. It is a skull of a Diplodocus, but it's not just a Diplodocus skull, it's a juvenile, it's a young Diplodocus, one of the big long neck dinosaurs. Now, even though those things are so big, their heads are actually pretty small and they're really fragile. The bones are so thin that they break very, very easily. So they usually don't fossilize at all. There are whole species of these kinds of dinosaurs that we don't even know what the head looks like. And we've not only do we got one, but it's from a young one when they're even more small and fragile. They're super, super rare, and it's absolutely incredible. And there's tons of cool things that we can learn from that. And I think that is the most significant thing that we have in our collection here at the Science Museum. It's awesome. Let me see if I can pull something real quick. Do we have just like 30 seconds to grab something here? We've got a fun few projects. So I'll be right back, guys. Aaliyah, if you want to kind of fill the conversation here, I'll be right back with you.
I'm going to fill the conversation while Alex is coming back. And I'll just tell you a little bit more about how great it is to work with all of our members and to have all of your support at the museum. So I'm just going to remind you again that if you're enjoying this event, we have so many other cool events coming up. So for example, every Monday, we'll offer a specimen spotlight. It's just a 1-minute little post from our curators about something cool in the collection. On Tuesdays, we have science story time. And actually this week, it'll be Alex reading a pop-up book about dinosaurs. That's on our member Facebook page. And it also goes out to our Vimeo channel. And here's Alex.
Hey, all right, so we should be good again here. So these are a couple pieces from fieldwork that I actually did this past summer. Despite the whole COVID thing, we're able to still get out into the field here in Minnesota at least. And if you go to certain parts of kind of more southeastern Minnesota, you can actually find these here. So these are fossil leaves from about 90 million years ago. So this is from the age of the dinosaurs. This is from New Ulm, Minnesota. And if you get into just the right spot there, you can actually find these things. Now, what's really, really incredible, and I'm not sure how well it's showing up on the camera here, but when you get fairly complete leaves, there's a really great type of study called a leaf margin analysis. Basically, you're looking at the types of leaves that you're finding there tell you about the climate there. So you can actually quantify, you can actually get numbers of how hot it was when these plants were alive. And this hasn't really been done for Minnesota yet. So we can actually, using these plant fossils, figure out what the climate was like back during the age of the dinosaurs. And that will really help us better understand kind of the long-term changes in climate that we've had here in Minnesota. And by complete coincidence, you can also find fossils and bones and teeth and stuff from the Ice Age and a little bit younger in about the same area in New Ulm, Minnesota. So we're able to hit two birds with one stone. It's really nice. So this right here is a good old bison femur. So we haven't actually been able to figure out how old it is yet. We actually have to do a specific kind of chemical analysis to figure that out. But they are hefty animals there, right? So you can get some good preservation in some of the creeks and rivers and stuff. So this is one that was just kind of had a little bit of it poking out here, just a little bit to let you know it was there. Dug into the sandbank of the river there and actually pulled out this very, very nice bison femur. One of the things this will also allow us to do is get a sense of kind of how old it was and how that growth trajectory happened. We know that it was an adult because we've got the ends of the bone fused on here. So that actually tells you that it's not a juvenile, it's a pretty good sized adult, and we'll be able to tell a lot more about its life. We're also finding a ton of these bones have scavenging marks. So we're seeing them getting eaten by other things. So that actually gives us even more information about the kind of animals that were around at the time. So a lot of these are not just really one fossil, there are multiple fossils in one, which is the best. So you can find out even more. And we are definitely going to be going back to that part of Minnesota once the weather clears up for us.
That is so cool. It's so fun to be back here in the lab, Alex. Thanks for hosting us. I've got one more question, and then I really think we probably should wrap up, although it's so fun to see all of you engaged and enjoying this presentation. Oh gosh, now I just got another question. Okay, we'll rip them through. We'll do like a lightning answer round. Can you talk more about Titanoboa? We love Titanoboa from Jack. Alex loves Titanoboa too.
Of course. So Titanoboa, if you don't know, is the largest snake of all time, about 42 feet long, which is longer than your standard school bus and weighed 1.25 tons. I'm very lucky to have been part of the discovery of that giant snake. So I did my PhD work in a coal mine in South America on the fossil crocodiles. Along the way, we found this massive snake. It was a relative of anacondas. It would have been a constrictor. Non-venomous, but trust me, it did not need venom to do damage because it would have been able to exert so much force that bone would have been like tissue paper, like just nothing, just absolutely nothing. It's the equivalent of having the Brooklyn Bridge piled on top of you. Like it's just, forget it. Bones don't even matter at that point. And it would have been big enough around that if you picture kind of your average door, kind of the average thing that you would walk through, as it was going through the doorway, the sides of its body would have been kind of scraping against the frame of the door. That's how big around this thing is. what we found mostly were the vertebrae, the backbones. We also found some ribs. From that, we were actually able to do some growth studies. Actually, this isn't even published yet, but you guys look at the scoop. So we know that these things were getting into their 40s at least, and possibly quite a bit older. And the other fun fact is we think that it's similar to modern anacondas, where it's actually the females are much larger than the males. So when we're seeing these really, really big Titanoboa, we're pretty sure that they're females as well, which is kind of fun.
All right, lightning round, super fast answers. We've got a great question here from Melly. How do you tell a rock shaped like a bone from a real bone? That's a question I have too.
Yeah, and this comes up all the time. So really it comes down to textures and patterns. So once you look at a lot of these things, you start to notice this little kind of dimpled pattern that you see in bone, or if it's broken, you should see the spongy inside of the bone. If you're not seeing either of those things, it's almost definitely going to be a rock instead. Honestly, it really just comes down to getting your eyes on these things a lot. We're actually hoping to get a good resource for you guys up where you can actually, you know, is it a bone or is it a fossil, is it a rock, that kind of thing. But a little bit of experience, but there is very good telltale signs that tell you for sure one way or the other.
Great. And now our last question comes from Kellen, age 7. Have you ever found a Spinosaurus?
Oh, Spinosaurus, I wish. So Spinosaurus is from Northern Africa, and I have not yet had the good fortune to do field work in Northern Africa. So because Spinosaurus is very specific to that part of the world, and I just haven't gotten a chance to get there yet, I've not found a Spinosaurus myself. They are very cool. I've definitely gotten my hands on Spinosaurus fossils, but I have not gotten to find one yet.
So much to see and so much to learn from the lab. Alex, thank you so much for being here.
Absolutely welcome. Thanks for coming, everybody.
And all of you, thank you so much for your membership support. Without your support, we can't do great work in programming like this. We can't offer educational experiences for youth, and we wouldn't be able to welcome you back to the Science Museum, which we will be doing very soon. So I hope you keep watching our website for that. I hope we'll see you at some more of our programs, smm.org/thanks. Thanks to all of you, and have a wonderful morning.
Thank you.